Hey everybody. So this is a video that's a little bit different in that it's something I'm super new to. So this is less of a tutorial and more of a, hey, look at what I did. And the reason that I did it is because I went farther than I really should on the Ersatz Ben Bessel function physical modeling project, and I'm trying to figure out how to build the whole thing in Gen, or at least the kind of resonator portion in Gen. There's a part two of that, or part one of that video in the link in the description down below, and whenever part two happens, I'll add it as well. But basically, I'm just going way off the deep end there. But I wanted to make this video just about the filter component, because if you remember from that other video, basically the way that physical modeling synthesis algorithm works is you have a multi-channel filter over across 16 channels, and then you basically feed each of those channels a different frequency and a different resonance amount. And by passing an impulse of noise into that filter bank, then you can get these timbres. So I was interested in this question of, okay, could you actually put those filters, which are implemented in Ben's patch using the SVF tilde MSP object, could you do it in Gen? Well, for that I would need the SVF state variable filter. And I tried using the one from generating sound and organizing time, and I wasn't getting it to do what I expected it to do. And I don't know if that's because I'm doing something wrong in the Gen patch, or if it's because that filter is different from the one from the SVF one. So I went to the SVF help file, and it says, SVF object is an implementation of a state variable filter algorithm described in Hal Chamberlain's book, Musical Applications of Microprocessors. So I went and found that, which is here, and on page, whatever we're on, 489, there is this digital state variable filter. And so I took this as an opportunity to get into an area that I don't normally get into and test out a practice that is described in Go, generating sound and organizing time, which is to basically take these kind of circuit diagrams and just rotate them 90 degrees so that the input is at the top and the outputs are at the bottom, and then just pretend it's a Gen patch. Because we can basically make a patch that looks a lot like this diagram in Gen. So I thought that would be a fun thing for me to try, and I think I got this right. I don't understand all of the details of it, but I figured it'd be fun for me to show you what I did so that you could go through the same process yourself. And for those of you that kind of understand filters better than I do, I'd love to hear your thoughts on any part of this. Like, why does this even work? Why does this give me a high pass, a band reject, and a low pass filter all in the same algorithm? Just any thoughts that you have are I think are valuable. But so this is what I'm going to show you, and let me just walk through this because it looks complicated, but it's actually more simple than you might think. So the first thing that we need to do basically is define kind of what these different shapes mean, the circle, the triangle, and the square, because they actually do mean distinct things. And there's kind of a legend here, which is that the triangle is an amplifier. So in this case, it's an amplifier of gain with a gain of negative 0.314, but you could also, of course, have a variable in here. So this we could always implement anytime we see an amplifier in Gen, we're just going to perform multiplication upon the signal. Here we have a summing kind of junction, or what he calls a mixer or an adder. So we have inputs that are all just being added together. And we can also, he specifies the sign of those inputs. So sometimes you would need to make the signal negative before it goes into this summer in order to make it so that that value is being subtracted from the rest of them. You could also use kind of a chain of plus and minus objects, but as you'll see in my patch, I do kind of copy this design where you just have, as many inputs as you need going into one inlet, because we know that that's always going to result in addition in Gen. And then anytime there's one of these minus signs, I just multiply the signal by -1 before it hits that junction. And then finally, we have the square, which will have this z-1 in it. and this is a one sample period delay. So this is an element that is necessary in a digital system because in digital audio, we're working in discrete time. So the gen patch, as I've said many times in these gen videos, anytime we have a gen patch, we have to think of it as executing itself for each frame of the computer's sample rate, 44,100 times a second, or what have you. And any time that we need to get the output of some process, either the final output of the gen patch or even an input of some object within the patch, and pass it upwards into an earlier part of the patch, then we need to capture the value at that point in the algorithm from the last sample frame. So if we go down to the diagram again, that concept will make more sense. So at the input, we have that coming in, and that's actually being summed with two things that happen downstream of that input. So we have the delay that is being implemented here and here. And it's not just a delay, it's kind of like storage. We're basically storing the last execution of the last execution of this patch, the value at this point. We're storing that and we're passing that back around in these feedback loops. And that's happening here. In this place, we're using that stored sample from the past frame in two places. We're passing it back around to form an integrator right here, and then we're also passing it back up this way. And then down here, similarly, we also have another example of an integrator. This one doesn't need it because we already, I believe, performed the kind of retroactivity right up here. So this one, we don't have to have another one of these. So basically the algorithm is we take the input, we add it to its output, we subtract its output from the input. And we also subtract from the middle here after multiplying by our Q value, which is the resonance. We then multiply the signal by the frequency and add that into, again, the kind of the integrator that exists here near the bandpass. And he even displays this concept of the integrator right here just as an isolated thing, because this is something that appears quite often within these systems, is this situation where you basically have an input and then the output getting added back into this input. And this is essentially exactly the same thing as the phasor integrations that you've seen me do many, many times, right? So very often if you saw the video on like clock modulation, as an example, I did one recently where we take a phasor, we use delta to get its slope, we mess around with that delta, and then we add those values back together using a combination of the wrap object and a history object. This is exactly the same concept. We're basically building what is essentially a running total here at this summation junction here. In this particular case, because we're dealing with an audio signal that's going to have negative and positive values, this doesn't just accumulate to infinity the way that it does in the case of a phasor. If you've watched my other videos where I sort of show that happening, again, going back to that clock modulation video, instead, because we alternate in some way between positive and negative values, we don't need to do any wrapping here or anything. We just, assuming the kind of the algorithm is implemented correctly, and these coefficients that perform the amplification, like the frequency and the Q, are not outside of their kind of allowed bounds, then these numbers won't overflow. They won't get too high or go into the, they won't go too far in either direction, positive or negative. So basically, I just took this diagram and kind of tried to reconstruct it. It's a little bit hard to explain it, as I'm sure you can already tell, because we're dealing with a system in which so many of the outputs are being fed back into the input. So it's quite difficult to kind of talk about it linearly, because from the very beginning, you're already talking about the output of it. But hopefully by listening, or by looking at this, you can get a general sense for what's going on. And so now let's actually go look at that in Max. So I have, I believe I have the screen grab, and then I'm going to open up my gen patch. And for now, we'll just take the Q and the frequency. There was some additional work required to actually convert a frequency in hertz into the values that need to be passed into these amplifiers. And actually the same for the Q. We needed to do some extra processing to those values, and I'll show you that at the end because that's actually further down in the paper. The inputs to this algorithm, or the sort of parameters, they're basically just the frequency and the Q. But this frequency is not a frequency in hertz. It's just a value, I think, between 0 and 1. So when we implement this to start without frequency, you're just giving it values between 0 and 1 for both of these. And then there's this kind of act of figuring out how to convert frequency in hertz and Q and kind of or resonance on a range that makes sense into the values that the algorithm needs. And if you've looked at some of the other like filter patches in generating sound and organizing time, you'll see that there's kind of a similar pattern here where very often, like in the case of a very simple one-pole filter, low-pass filter, like in the go.onepole.basic, I think, we have, this is a low-pass filter. This A is an amount that we're amplifying, kind of a feedback path within the signal. And you can convert from hertz into this value, but this value by itself doesn't really make a whole lot of sense in terms of frequency or pitch. So you kind of have to perform a conversion there. So this is perhaps the most simple type of filter. And the same thing happens where you have to kind of get from a frequency to this amplification value. So we'll leave that aside for now, and I'll show you that in the paper when we get to it. But basically, I just did the best that I could to try to copy this algorithm. So we have, in place of all of the sum junctions, I'm using the pass operator in Gen, and all pass does is just passes through its input to its output. So instead of using the plus object, I'm using the same kind of convention here that we just have multiple inputs going into kind of one space. And we know that always in Gen, when you send multiple inputs into one place, they are added together. So we have this is this summation. We then multiply by the F value. So that's what's coming through over here. We then have our first integrator. So that's this section here with the bandpass. And you can see that we take out the bandpass here, as well as the high pass up here just below the first summing junction. So the history D1 here is this, basically this Z minus 1 here, because in his paper, he describes how to implement this in BASIC, I think. Yeah, in BASIC. And so he uses D1 to describe the sample, the delayed sample associated with the bandpass output, which is right here. And then D2 is the one down here associated with the low pass output. So I just labeled those histories to make them a little bit more clear. So that's the first one. I discovered some problems where I was getting not a number, nan, that seemed to be originating from these integrators. So I put a fixed nan, which basically turns a nan into a 0. I don't know that this is strictly necessary because I think that one of the reasons that it may have been happening is because I was sending in amplification values here and here that were invalid for this algorithm, because you do have to be careful with these kinds of things that the numbers that you're amplifying by do not go outside of the bounds that are kind of allowed, quote unquote, by the by the algorithm. But once I had these in place, they seemed to make the thing less likely to like freeze or explode. So I just left it in place. So that's the first integrator. We then multiply by the Q here on a feedback path back around to the summer up here at the top. And we've already done the delaying with this history. So that's what makes this path possible. If this were not here, this feedback path would be impossible. We then scale again by the frequency, and then we go into another integrator, which is this guy here. And then we sum the output of the high pass filter with the output of that integrator, and that gives us our band reject. And then we take the output of the final integrator, and I suppose this part is not necessary. We send that to the output as the low pass filter and loop that back around into the top summer. I am noticing that, so I don't know how much these details matter, but you'll notice here that anytime we have one of these accumulators, we can either choose to take the output from the history, from the delayed portion, or from the kind of non-delayed portion, right? Because at any integrator, we're getting the current value that this algorithm is able to produce here, and then basically the past value that this little system produced is going to come out of this outlet, and those are being added together. So if I take this output, then, oh, sorry for the clicks and pops there, then I'm getting that sort of past, the like one sample frames in the past output of this little system. So I tried to kind of be as true to the algorithm here as possible, where here we actually do take the historical frame, but here we don't. And that all seems to work. And so there was a little bit of detail there where I had to really make sure that I was getting every little one of those details correct, because it wasn't quite working. And now that it's working, I'm not going to mess around with changing it. Okay, let's hear it. So I have two samples here. One is just a burst of noise, so we can start with that. And then the second one is like a sample. So starting with the burst of noise, and we can start with the low pass filter. And we're at 6,400-ish hertz. And now if I sweep this down, we're getting filtering. And also we have a resonance. Which is cool. And now let's test some of these other outlets. So let's try, the first one is the high pass. So let's test that one. That one sounds good too. And again, we can get resonance. We can also try the band pass. And then there's also a band reject, which is the opposite of the band pass. And then let's say the band pass, and we'll turn off this noise, and we'll try it with an actual sample. And I'm going to turn this down a little bit just in case it's too loud. And it has a weird The resonance has a very weird kind of smeariness to it. So let's, as a final piece here, let's just look at how I derived the correct F and Q in the algorithms from the F and Q parameters that I have here. And for that, we can go back to the paper briefly. So let's see, tuning relationships. In order to use a filter, it's necessary to know the relationship of the frequency and Q determining factors, F1 and Q1, and the corresponding actual physical parameters. Q1 equals 1 over Q, which has a useful range from 2, corresponding to a Q of 0.5 to 0, which responds to infinite Q. So Q is the parameter that we control. Q1 is the input to the algorithm. So if we go back to Jen here, we are, first I discovered that while I wanted to have Q on the range of 0 to 1 in the patch for control purposes, that this value, because we can go to infinite Q, right, should go from 0 to like some bigger number. And I just played around, and 100 sound readable, 50 might even be better. You know, it's just a question of like, what's the sort of like maximum amount of resonance that you want. And this might also be a place where putting some kind of like exponential shaper could be valuable, right? Where maybe you want a little bit finer control at the lower end of the range. And to do that, you would basically add a exponential unit shaper right here. So scale to the range of 0 to 100. Make sure that it doesn't go actually to 0, because we're going to take 1 over that value, and we can't have 1 over 0. And then we clip that to the range of 0 to 2, because it has a useful range from 2 to 0. So that is all seeming to work. And I really had to just trial and error this to like sort of translate from like what this says to what I have here. And then there's the frequency, which is a bit more complicated. Center frequency relation is a little more difficult and a little less ideal. And this was a lesson in reading the whole paragraph before trying to dive in, because for a while I was messing around with this equation, but it was not yielding good results. And that's because, unfortunately, the relationship is not exact with the error getting, where it says the center frequency approaches 1/2 the sample rate. And there's this explanation of that error. And then I finally made my way down lower and discovered that this is actually the formula that you should use. So F1, the input to the algorithm, is 2 times the sine of pi times F. So this is the actual parameter that we pass in, so the frequency in hertz, and then this is the computer's sample rate. So if we go back to Jen and look at how that was done, divided by the sample rate. So with these often like times equations in Max, you kind of want to work backwards within them, or like from the inside out, I guess we could say. So if we look at this again, we want to basically do the frequency in hertz divided by the sample rate times pi, take sine of that, and then multiply that by 2 in that order. So divide by sample rate times pi, sine of that times 2, and that will give us the F1 that we need to pass into the algorithm. I know that sine is a little bit of an expensive operation. So I was asking in the Max Discord about how to do this better, how to do this more efficiently. There's a few ways, and I'll actually just go to my post. So I said, hey, is this a reasonable substitute for sine and cosine? Because cycle is a sinusoidal oscillator. It produces a cosine in response to not really an angle, but like a phase. So a value on the range of 0 to 1. And then I was thinking, you could then make sine by just doing a phase shift of 90 degrees or 0.25, and then wrapping that within the range of 0 to 1. This is actually not correct because the modulo here doesn't behave on the negative number the way that, let's say, the wrap operator does. So I corrected myself down here. But then also Graham, one of the authors of Go, came in with this really cool approach where basically you just pre-compute the sine and cosine when the patch loads, and then you just stick it in a buffer. And data is a type of buffer that is specific to Gen, that is basically a buffer that is not exposed to the parent patch. So it's just a buffer that kind of is exclusively reserved for that Gen instance. And so we can say, we basically create the data. It has two channels, one for cosine and one for sine, and it has 4,096 it's 4,096 samples long. This ready is basically going to tell us whether or not we're going to compute those sines and cosines and stick them in this buffer. And we know to do that if the elapsed, which is a Gen, like Gen's signifier for the amount of time in samples that this Gen patch has been running. So this is a really useful way to basically know, like, when elapsed is equal to 0, that's the very first sample that this particular Gen patch has been executed. And so it's a great way to be able to initialize things. So when elapsed is greater than or equal to the length of this buffer, we're saying ready. And ready actually means we have successfully completed this process of calculating the cosines and sines and putting them in here. And if we're not yet ready, meaning we have to continue to put stuff in here, we're going to take that current sample index, which is going to be some number between 0 and 4,096, multiply that by 2 pi, and then divide that. So it's elapsed divided by the length of the buffer. So a normalized value between 0 and 1, multiply that by 2 pi to get a value in radians, and then just take the cosine and sine of those and stick them into the first and second channels of this cos-sine buffer. And then later, we also just report to the output, hey, this is done. And then later you can just use a peek operator to look up the sine and cosine. So this is kind of a cool little extra tidbit that I learned from Graham through this process, which is just a super efficient way to be able to get sine and cosine. And why don't I just add that in now? Let's actually try that, because I didn't actually do it. So data, cosine, all of this stuff. We can, let's do an out 5, I think, yes, to know if we're ready. And then let's go back to the main patch here, and I'll put a live.scope on that 5th outlet. And it's telling us we're ready. I'm going to restart this, and we should see that there's a little stair step in here. Although that might have been so fast that, or maybe we got an error here. No, we're good. Okay, so let's try and see if that worked. We didn't see the 0, but it may just have been because it was so rapid. The other thing is that maybe this didn't actually reinitialize in the way that I thought. So I'm going to copy this, and then I'm going to paste replace. There we go. Right. So you see that. So now this data cos-sine has cosine in the first channel and sine in the second channel. In this case, we only need the sine. So we only need the second channel. So here, we can actually get rid of the scaling by pi, because we're not doing this in radians anymore. We're doing it on the range of 0 to 1, but this is actually on the range of 0 to pi. So I think we need to divide by 2, right? Because normally, like if we go back and look at the gen patch, it's times 2 pi. So if I wanted to, I could actually just multiply by pi here, and then have sine and cosine over the range of 0 to pi in the buffer. But I'll leave it how it is. And instead, I'll just divide by 2 here. Or perhaps a bit better, I'll multiply by 0.5. And then I'll say poke cosine 1, I think. Because I think that first argument is going to tell the name channel, right? So yeah, that's the channel. And you know what, before we do anything in terms of passing this into the actual, oh, not poke, but peak. I broke the, so I wrote some stuff into the buffer here, so I need to correct that. But before I actually try to pass that into the actual filter, I'm going to send that to the ready outlet just to make sure that I got it right. And again, I'm gonna copy this, and then I'm gonna paste replace. Okay. And now we should see that if I change the frequency, oh, I need to use wave, not peak, because I'm on the range of 0 to 1 rather than on the range of 0 to 4096. I could also scale this value by, I could use peak. That was so silly of me. I could scale here by the range of 4096 over 2. Let's see now what happens. Yes. Okay, there we go. Okay. None of this is that important, just a little bit of optimization. Really not that important, but a fun opportunity to learn. And this whole thing for me is just trying out stuff I don't really do very often in order to learn new stuff and get better at what we all love to do. Cool. All right, that's that. I'm going to try using this inside of the AirSats bin physical modeling thing. I don't know if it's going to work or not. We'll find out. If that video doesn't come for a while, it's because I'm struggling with it. But yeah, maybe it'll come along eventually. And if not, then you'll have this nice little demonstration of what it's like to be me trying to implement a state variable filter in Gen from a book that came out a really long time ago, 1985. So, pretty cool. All right. Thanks for watching. I'll see you next time. Bye-bye.